LeetCode Problem 53, Maximum Subarray, is more than just an interview staple. It mirrors real systems like finance dashboards, sensor feeds, and analytics engines, where tracking peak performance in real time matters. Brute force works in theory, but it bogs down fast. So how do we streamline the search for the biggest subarray sum? Let's dive right in. Time to waddle through every possible subarray. We're starting with the simplest route, brute force. Let's drop that into code. First, we'll declare a variable to store the highest subarray sum we've seen. Since we're hunting for a max, we kick things off with the lowest possible value. Our outer loop sets the starting index for each possible subarray. This anchors where we begin collecting values. Each time we pick a start, we reset a sum tracker. This will hold the running total as we stretch the subarray forward. Now comes the inner loop. It grows the subarray one number at a time. Each new element gets added to our current sum. At every step, we check if our current total beats the best so far. If it does, we update our max, always keeping the top score in sight. Once we've tested all subarrays, we hand back the best result. That wraps up the brute force strategy. Brute force hits big O of n squared time. For 100,000 items, that's up to 10 billion operations, a storm of loops for one little duck. Space stays constant, big O of 1, and there's no risk of overflow unless we cross into giant sums. But we can do better. What if we remember the best subarray ending at each index instead of recalculating everything? That's the idea behind dynamic programming, and it's way smarter. We'll build a DP array where each spot tracks the best subarray sum ending right there. Since every subarray has to include at least one number, we initialize the first index with the first input. That's our starting case. Then we set our global max to that first value, so we've got a baseline as we fill in the rest. As we move through the array, we choose start a new subarray at the current number or extend the previous one. We go with whichever gives the bigger sum. Once we calculate the new total at this index, we check if it's our best yet and update if needed. After scanning all elements, we return the highest subarray sum we tracked. This cuts time down to big O of n, one clean pass, but we do pay in space, big O of n for the DP array. If you're in tight memory systems like embedded code, that trade-off matters. Let's tighten it even more. Since each decision only depends on the last, we don't need a whole array, just two variables. Let's bring the space cost to 0. We start with two trackers, one for the best total so far and one for the best subarray ending here. Both begin at the first element, since that's all we've seen so far. Then we sweep through the rest of the array. At each number we choose, extend the subarray or restart fresh. Whichever gives a higher total wins. With the new subarray sum in hand, we check it against our global max. If it's better, we update it. After testing all options, the best overall subarray sum is ready, and we hand it back. Kadane's algorithm delivers big O of n time and big O of one space. Just one pass, no extra storage. That means it scales smoothly, whether you're scanning 10 numbers or 10 million. Clean, efficient, and battle-tested, it's a favorite at companies like Google and Meta. So what did we build? We started with brute force, slow, heavy, and full of repeated work. Then came dynamic programming, faster, but still holding extra memory. Finally, Kadane's algorithm gave us a lean, elegant solution with no wasted space. It's more than just a LeetCode trick. It powers real-time systems, financial tools, and performance-critical code. If you're chasing roles at top tech companies, this kind of thinking sets you apart. Find ways to apply it, practice often, and keep leveling up.